Okay, let's look at this November 2019 question on internal resistance. It says to you, in the circuit diagram, resistor R with a resistance of 5.6 ohms is connected together with a switch, an ammeter, and a high resistance voltmeter to a battery with an unknown internal resistance, little r. The resistance of the connecting wires and the ammeter may be ignored. The graph below, here's the graph over here, shows the potential difference across the terminals of the battery as a function of time. At time t1, switch S is closed. So you can see, if you have a look, here is where the switch is closed over here. Okay, so before the switch is closed, can you see the voltmeter here? Before the switch is closed, the circuit is open, so the only thing the voltmeter can be reading is the EMF of the battery. So this value here, 13, is the EMF of the battery. Okay, when they closed the switch over here and completed the circuit, in the circuit we just have this one resistor R. So the moment you complete the circuit, this must now be the terminal potential difference. Okay, so we know the EMF from the graph, and then it immediately drops. Why? Because the battery's got an internal resistance, and the internal resistance uses some of the energy, and so the volts are lost to the external circuit. So it says to you, define the term EMF of a battery. Remember, this EMF definition is not necessarily in the grade 12 guidelines. So the definition is here: the maximum energy provided by a battery per coulomb charge passing through it. So if we wanted to make it specific to this question, this battery provides 13 joules of energy per coulomb of charge passing through it, because this battery has an EMF of 13. Then it says 8.2, write down the value of the EMF of the battery. EMF is when no current is flowing, so the EMF is 13 volts. Now it says to you, when switch S is closed, okay, so that's the second half of the graph, it says calculate the current through resistor R. Well, we know that the moment that you close the switch, the terminal potential difference is 10.5 volts. So this battery is only supplying 10.5 volts to the external circuit. So we're going to use V equals IR, or however you like to put this formula, but I always think of it as V equals IR, okay, or R equals V over I. And I'm going to put the voltage is now only 10.5 volts because of the internal resistance of the battery, equals the current, which is I, times the resistance, which is 5.6 ohms. So if we work this out, it's 10 divided by 5.6, and I get 1,875 amps. Now that's quite a nice round number, so I like to leave it like that. So I will be using 1.875 in the rest of my calculations. But if you wanted to round it off to 2 decimal places, remember it says a minimum of 2 decimal places, so we could actually leave it at 1.875 because 1.88 is the minimum. Okay, now it says to you, calculate the power dissipated in resistor R. So we always use the word dissipated when we talk about power. It's like, how's the energy being used up? So it's just saying find the power. So if you go look on your formula, you have on your formula sheet, if I show you here, you have a bunch of power formulas. If you have a look here, power equals work over time, because we know power is the rate of doing work, or power equals VI, or power equals I squared R, or power equals V squared over R. So you can pick any of these formulas. If you want to be really careful, use only the things in the question, and in the question they give you V and they give you R. Remember we read V off the graph and R is written on the resistor, but the easiest one is P equals VI. So if we wanted to, we can just go P equals VI because we just calculated I. Okay, so the volts were 10.5 off the graph and the I was 1,875. So the power is going to be 19,688 watts because power is the rate of doing work and we measure it in joules per second or watts, or 19,69 watts if you like. And there's a range of values in the memo in case you rounded when you rounded or not. Now it says to you, calculate the internal resistance little r of the battery. So we know the EMF is equal to IR plus I little r, okay? So we know that from the voltmeter, from the graph, when no current is flowing, the EMF is 13 volts, okay? And now we know that the current is 1,875 and the external resistance is 5,6 ohms, okay, plus 1,875 times little r. Because it's a series circuit, the current is the same everywhere. So if you do some maths here and you work it all out on your calculator, you will get the small resistance to be 1,33 ohms. Okay, so now we have the internal resistance of the battery. Now the question goes on and it says to you, two identical resistors, each with resistance X, you can see them down the bottom over here, X and X, are now connected in the same circuit with the switch S closed as shown below. The ammeter reading increases to 4 amps. So if the current has gone up, it means you're going to lose more volts in the battery, because remember, the battery uses the current is doing work in the battery on the internal resistance. So if the current has gone up from this 1.88 amps to 4 amps, that means we're losing more voltage. So the voltmeter reading is going to decrease, okay? It is decreasing because the current went up, and when the current went up, the internal resistance increased. Remember, it says give a reason for the answer by referring to V internal. So V internal increased, so the voltmeter, which is telling you what is being delivered to the external circuit, is going to show you a lower reading because of more current going through the battery's internal resistance. Then it says to you, calculate resistance X. So if we have a look here, okay, if we have a look here, what is going on here? We have a parallel circuit. Can you see the circuit is branching out and it is a parallel circuit? But these two resistors X, they are in fact in series with each other, okay? So I've got two resistors in series. So the total resistance for those two resistors is going to be 2x, because if resistors are in series, we add them together. So I then have 2x in parallel with R, okay? So we take these two resistors, pretend they're one resistor with a resistance of 2x, and then that is going to be with little r. So we take the formula for internal resistance, okay, EMF, because we know the EMF equals IR plus IR, okay. So we know the EMF is 13 from the graph in the beginning, and now they said to you the current has gone up to 4 times the external resistance plus 4 times the internal resistance, which was 1,33 ohms, okay. So then by algebra here, 4 times 1,33 is like 5,33. So 5,33 from 13 leaves you with 7,666 equals 4R. So then R is going to equal 1,92 ohms. Okay, something like that if you put it all in your calculator. But now remember, this is R, that is for the whole external circuit. Okay, so I'm going to come work up over here. Don't get confused. So in the external circuit, okay, I actually have a parallel connection. Okay, so 1 over RP equals 1 over R1 plus 1 over R2. Okay, this thing when it pops up is very irritating. So if I have a look here, what is my 1 resistor in my parallel circuit? It's 2x. Okay, so 1 over 1,92. Remember, I've just calculated the whole external resistance in the previous calculation. 1 over 1,92 equals 1 over 2x, because those are the two x's in series, plus 1 over 5,6. Okay, so then I end up, just put it in your calculator. Remember, you people are not so lacquer good at fractions. Put it in your calculator and you work out that x is something like 1,46 ohms. Okay, remember that this is a 1 over formula, so you will end up with 1 over 2x. You must invert it, and then that will give you the value for x.